I want to start today with some homework and participation comments. And I know a bunch of you are, a little bit nervous about your grade and stuff. And then we're going to talk about some interference demonstrations up here. And then we're going to finish class with some Coulomb interaction. In other words, the electromagnetic interaction. And finally, before if there's time, we'll talk about exam 3. But exam 3, it's basically everything up until today. So, and same procedure as last time. Now, what I want to mention concerning your participation data, as of Tuesday, there were 65. Now, we're going to do some clicking today. So that's going to change in about 2 seconds. All right? But here's how it looks. Can somebody calculate 65 times 0.85? That's the 85% mark. So that should be about 50 something. 55 point what? 55.25. All right. So that's 85%. So if you have 56 or more answers on the books, you have 25 out of 25 clicking. If you have less than that, you got to do the proportion. And so 65 questions, and actually I counted up how many lectures that we've done clickers for, and it's 17. Well, we did about 4 lectures before in August, and then but 17 official clicking lectures, and that's not including exams. We've done 2 exams with clicking, and you guys have done pretty good. So it's almost 4 per lecture. And so what that means, you know what we can do? So right now we've got 65. You have to have 56 or more to get 100%. So that means there's 9 points to burn. You listening? You guys? 9 points to burn. That's roughly 2 lectures. It's 2-point-something lectures. So that's why I say, if you've missed, just 1 lecture this semester, chances are you're still okay for 25 out of 25. If you've been to all the lectures, of course, and clicked, you're golden. But if you miss more than 2 lectures, then you're going to start to feel it in your participation points. All right. Now, I'm going to do a roundup today after class. So it might be 70 today. We might be, depending on how many questions we get to today, we might be up to 70. But whatever the number is, I'll do a roundup and post it in your grades page, first of all. And then in discussions, I'll put a new thread in discussions to show you, how to handle it if you're below the 85% threshold. All right, and most of you are doing quite nicely. A few of you have tripped up a little bit. Oh, you know what else? Let me make another point to you. We have some bonus point activity coming up. All right, now we don't do a whole lot of bonus points. Sometimes I put 51 points on a test, and so like 1 bonus point if you get it right. But we're going to have 2 bonus point activities that everybody can take part in. So in other words, if you did, hey partner, the cowboy hat's looking pretty sharp. If you didn't get any early iClicker registration, you can still get some bonus point from the stuff that's coming up after Thanksgiving. And traditionally, what we do in the last lecture, so I think that's November 30th for us, the last Thursday of November, the last 30 minutes or so of that lecture, I give you a review sheet, and you're going to click it in like you're doing a test. So you'll work with your neighbors, and just do it at your own pace, and then after you finish it, you're dismissed. So it might be 15 questions, maybe 1 or 2 calculations, and you'll do it in the last 30 minutes. And what I'll do is convert that into up to 4 bonus points. That's traditionally what I do. All right, so if you're in that lecture and you didn't get any of the early registration bonus points, you can get some of those for just coming and doing your clicking. But you got to get them right. So if you get 100%, you get 4 points. If you get less than that, you might get 3, 2, or 1 point, or 0 if you don't come. Second, that weekend after the last lecture, you'll have a mega review homework. It'll be ginormous. And it just, another study tool to get you ready for the final. All right? And that one will be in web courses. And so it might be 25 questions, and it might be a few more calculations and a few more concepts. And I'll convert that to 4 points of bonus pointage. All right? So if you've missed some lectures for whatever reason, or your clicker pointage is a little bit low, or your homework, you can still snag up to 8 bonus points after Thanksgiving and kind of help out your grade. And I know everybody, and these ones, everybody will have a chance. Okay, so even if you couldn't get your clicker on time. All right. So anyways, the clicking data is I'm going to try to get that rounded up this afternoon after my noon lecture, or after my 10:30 lecture, and then start posting it. Another thing is homework, and that one is a little bit easier to calculate. It's just a straight percentage. We'll do that right now. Let's do a little rundown on the homework. Now, yeah, message failed. Something's wrong with my phone. Let me turn this off. Hold on a second, you guys. Okay. As of this morning, we have 295 possible score points homework, and that includes 74 over in the Great River Learning website in the mini reviews. And yes, the mini reviews are now active, Chapter 6 and Chapter 7. And so from Chapter 2 up to Chapter 7, that's 74 dineros. Plus we have a bunch in web courses, and altogether they add, right as of today, they add up to 295. All right? And by the way, if you look at your grades page and your Great River homework rows have a -1, and you know that you're in there and you've done the reviews, what that means is either you haven't typed in your NID, you've typed in your UCF ID number, not your NID, and we need the NID, or a few of you are in the wrong section. You registered for Section 2 accidentally, and you're supposed to be, this is Section 1. All right, or you might be in the online section, the W59 section. So you got to rectify that. And there's discussion threads about how to do both of those things. All right, so now we've got a fairly large homework coming up this weekend to study and get ready for Exam 3. Because we didn't have any homework Tuesday night, so we're going to have some this weekend. And, so you have something to work on. Get ready for Exam 3. I was in office hours. I had a bunch of students. We had a good office hour session yesterday, and just talking about, things. And there's a ton of different calculations that I can feature on the iClicker part of the exam on Tuesday. Now, the exam's not written, so I don't know what I'm going to put on there. But if you think about it, I could put a wavelength or frequency calculation for the speed with the speed of light. Heat, melt, heat, we've done a ton of those. Thermal equilibrium, we've done a ton of those. What else have we've done? several other calculations. So there's a good array. Now you guys might not see, you might see 2 calculations. And you might see some cinchy calculations in the multiple choice Scantron part. So that's always a possibility. All right, so this homework coming up this weekend, it might be 20 points. So if it is 20 points, that would bring us up to 315. All right, now I'm going to give you some examples using this hypothetical 315. We might be only 310 over the weekend, or we might be 318 or some other number. But if it is 315, here's how it's going to work. You know, you take your score, divide it by 315, and then multiply that by 25. So it looks kind of like this. Okay, so here's an example. You have 288 homework points, Great River plus web courses. And so what you do is you divide that by 315 right here. Okay, here's your quotient. That's your percentage in the square brackets. Multiply that by 25. Okay, that's this next one over here. And if you do that multiplication, you get 22.86. And then remember, always for homework and for participation, always round up. Okay. Now, if you're typing in an answer for a test question about a wavelength or about a thermal equilibrium temperature, round up or down to whatever's nearest. You know, do your rounding carefully. But for homework, I always give you guys the benefit of the doubt and round up. All right, so that's how you do that. Now, questions about this before we get back into interference concepts? Okay. By the way, one more comment. I sent out Exam 2 PDFs yesterday for everybody that wanted one. And if you look in your grades page, you'll see a little, it's attached to the Exam 2 Scantron row in your grades page. There'll be a little balloon like a comic strip icon. And then you click that and you'll see your PDF. And it'll say something like, this is your Exam 2 PDF. And then it's attached to you, your PDF file. All right, so you can look at that when you get a chance. And on that same note, I have to put up the blurb sheet now for you guys. And I'll try to do that. Whew. I won't do it today. Maybe I'll do it tomorrow. All right, let me ask you some questions on the clicker using interference or about interference we talked about last time. I'm going to ask you about a particular spot marked with the X out in the North Atlantic. You know, and last time we talked about, you know, 2 storms, one off the coast of West Africa, so that would be over here somewhere, and one off the coast of Nova Scotia. See how close they are together? Did you know that Orlando, here's something interesting you may not have thought about. From Orlando, that's off the map. Orlando's down right about here. It is closer for us to go by plane from Orlando to Greenland than it is for us to go from Orlando over here to the Cape Verde Islands. All right, and yet Cape Verde Islands and the weather down there affect us in Orlando like crazy. You know, because that's where, for instance, hurricanes come from. We don't care too much about what's happening up in Greenland. But Greenland's way closer, 1,000 miles closer, approximately. Anyway, so we got this question. All right, here's your first clicker question for today. At this point in the North Atlantic, X marks the spot, 2 waves meet at 2:07 and 12 seconds a.m. this morning. They're in phase, crest to crest. So this produces what? A, B, C, or D? Read carefully. And this is like a question you might see on exam 3. Matter of fact, I could give you a map, like a line drawing of the North Atlantic, and put an X in it, and then ask you like 4 or 5 questions based on that map. So, okay, 20 seconds to vote, starting right now. Ten seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, good. And yeah, the answer for this one, most of you got it right, is D. And the competitor is A, but A is half true. You do get a doubly large crest, but not because of destructive interference. You get it because of constructive interference. So this is kind of a 2-part question. I should actually, if I was doing this in web courses, I'd make this a 2-point multiple choice question, because you really have to get 2 things correct in this. All right. Now, you can put your clickers up for now. I want to do some demonstrations here. All right. The first one that we're going to do is beats. All right. Let me move this stuff out of the way. Let me move this out of the way here. All right. Now, these are... I'm going to put my headset down here so that I can get... this to record. And I'm also going to activate this microphone. Okay, I'm going to put this microphone right here, right near the headset. All right, and that way you'll be able to hear it, and with the headset it'll also go into YouTube. All right, now these are both tuning forks. They're identical tuning forks. And so that means, because they're identical, they'll put out the same tone. All right? That's the first one. Here's the second one. All right? Pretty much identical. It's the second one. See that? That's a resonance. All right. Now, when I hit both of them together, just listen to them. Double, everything's good. You're hearing 2 waves, same frequency, same wavelength. Just sounds a little louder. Now, I'm going to attach this little metal clip, okay? And it's just a screw-on clip here. And what it does, it adds a little bit of weight to the one tine of the tuning fork that I attach it to. All right? Now, here's the unweighted tuning fork. Okay? Here's the weighted tuning fork. Let me get this. They're not quite, this one's off pitch a little bit. Let's try that again. Here's the regular unweighted tuning fork. Hear that? Right, now let's do them both together. And what you're going to hear are beats. Okay, and hopefully it'll feed into the YouTube properly. Here we go. Actually, my microphone here. All right, here we go. Listen. Hear that? That's beats. That again. Listen. Okay, that wobbling, that's beats, that's the beat frequency, and the beat wavelength is a little bit longer. Now, let me ask you an IQ test question. Just a wild, crazy guess. If I bring this weight all the way up here, what will happen to the tone from this weighted tuning fork? Will it be lower pitch than it was before? Okay, so we know it's off pitch right here in the middle, where I had it. It's off pitch a little bit lower than the unweighted one. Will this make it lower or higher or closer to the unweighted one? Make it higher. So to be so if I do this one here, it'll be more like this, right? Okay, that's what your prediction is? Well, let's see what your prediction amounts to. I need a system because I have to. Oh my goodness. Let's do beats. See, because that's definitely lower, not higher. Let's do beats. Now, the frequency here is going to be further away. So the beat frequency is going to be a little bit larger because the difference is larger. Let's try it again. It's kind of hard to hear the beats because they're so far apart. Now, let's bring this all the way down, closer to the bottom. Now this is going to be closer to the pure, to the unweighted one. So here's the unweighted. Okay. Here's the weighted one, but with the weight all the way down towards the bottom. Pretty close. Let's see what the beats. Okay, that's closer to the middle now. So this should be a little bit higher beat frequency. Yeah. And then up here, if I put the weight all the way up here, it's so, the frequency is so high you can't detect the beats. Whoa. So that's beats. Now here's what the police do. They listen for beats with their radar gun. Oh, I was going to give you the formula for the beat frequency and for the Doppler shift. What the police officers make use of is the Doppler shift. If a source of radiation or sound waves is moving away from you, the frequency is lower. Kind of like if you ever hear an ambulance or a train go past you, they're blowing their horn, and it'll sound like it's a high pitch, and then as soon as they go past you, it'll go dip down a little bit in its pitch. That's the Doppler shift. And you can measure that with electromagnetic waves. And if the source is coming towards you, the frequency is higher, if it's sound waves or electromagnetic waves. And so here's what the cops have. Inside their radar gun, they have this. This is the factory setting. Perfect oscillation. What you send from your car is this. All right? And what they measure is the beat frequency. And then they convert that into your speed. And hopefully you don't get a ticket. All right, so that's beats. Now, I need a volunteer from the audience to come up here on the stage and help me with this next demonstration. Who wants to help? Come on. Okay, you come up and help. Come on. Okay, Mr. Big Time. You're volunteering somebody else. You come on up here. Come on up. And what we've got here is, come on up here. This is a coil spring, and one of the nice things about it, okay, I want you to hold this right waist high, and just hold it real static. Back up over here. Okay, face me. Okay. Now, what we've got is a spring. Let's move forward a little bit so everybody can see. Okay. And I can send a wave from me, and what's your first name? Philip. From me to Philip. Nice. Right, pretty simple. It goes to Philip and then it reflects back. He's keeping his hand fixed, so the wave kind of reflects off him. It doesn't it does. It comes back this way. All right? So now if I keep sending waves, whatever reflects from Philip is going to come back towards me and interact and interfere with whatever I'm producing. And if I do it at the right frequency, go ahead and make a sketch of this. This is called the fundamental mode. Don't laugh. Make your sketch a bump and a dip. Okay? And it's oscillating. This is a standing wave. This is the lowest frequency. It's called the fundamental mode. And it's a standing wave. And believe it or not, this is important for the periodic table. Now, you stay where you are. I'm going to change my frequency. That was pretty low. If I go a little bit faster, notice I don't really get anything, good there. But if I get just the right frequency, I can hit another standing wave mode. This would be called the first harmonic. There it is. Two bumps, a bump and a dip and a bump. Go ahead and make a sketch of this. This is the second excited, this is the first excited state. Okay? And it's a higher frequency. All right? And the fundamental mode was lower frequency, that was higher frequency. Now, let me see if I can get the next mode. And this one's tougher. The second excited state. Now this is the fundamental or ground state. And this is the first excited state. Now you gotta get it just right. There we go. No. Okay, that's it. Oh man, it's tough. Back up a little bit. A little tension. There it is. Whew. It's kind of hard to keep it. Let me try it again. Try to get the sketch. It'll be two bumps and a dip or two dips and a bump.
And what's that one called?
This is called the second excited state or the second harmonic. Okay. Philip.
Yes.
Thank you.
Oh.
All right. Let's give Philip a hand. And students, as I mentioned, standing waves, they're actually interference effects. Let me go back to the headset, turn off this mic. Okay. The standing waves are actually important for us when we're studying the periodic table. Now, I want to go onward to study the electrical force that holds atoms together, protons in the nucleus, binding an electron into an orbital state. Now, you've all seen, hopefully you've seen pictures like this one, where you have an electrical generator, that metal sphere, and if you touch it, if your hair's dry and you don't have a lot of conditioner in it and stuff, and if your hair's fairly long, your hair will fly out into the universe like this. Here's another one. Okay. And those two images, so here's her hair is really flying out. Those two images are from some other college, but this one is from UCF. And if you look at this is a student that was visiting UCF a few weeks ago, and I took this photo. This is the photo I was trying to get at the beginning of class. Okay, and you can't see the Van de Graaff generator, but you can definitely see her hair flying out. Okay, and sometimes I bring the Van de Graaff into the lecture hall and demonstrate it. But we had these demonstrations today. Maybe after Thanksgiving we'll do a demonstration. It's called the Van de Graaff generator. And there's Professor Van de Graaff from MIT. He's the guy that invented it. And here is Professor Van de Graaff standing next to a fairly large Van de Graaff generator. And all it is it's a metal sphere where the electrical charge accumulates, and there's a belt that goes from the bottom down here. You can see there's a little motor down here. And there's a mechanical motor, and it drives a conveyor belt, and the belt goes up into the sphere and then back down, then back up in the sphere. And there's a little bit of a friction device in the sphere that connects, it has an electrical conductor, a wire, to the sphere, and it separates charge from the belt that's moving by friction and puts it on the sphere. Now, that's Professor Van de Graaff. Here's a really big set. This is up in Massachusetts, nearby MIT, where they invented this. These things, see these those are two adults down here in the lower left. So these things are big. And we still use Van de Graaff generators for creating strong electric fields and accelerating charged particles like protons and electrons, atomic nuclei, and smashing them together. Those big atom smashers that you hear about, like the great big one over in Geneva in Switzerland, they don't use Van de Graaff generators over there, but what they do is the same thing. They smash atoms and stuff together. Okay, so this is a famous example of static electricity, static electric charge, which we're going to talk about. Now, I want to bring your attention to one more really helpful tool that you can start looking at. That's webelements.com. It's a really good periodic table, and you can click on any element and read all about each element.
What was the Van de Graaff generator?
Before World War II. Yeah, see, these pictures are black and white, so Professor, look at that. I mean, that's the vintage of, and he died in the 90s, I believe. You can look it up. But yeah, Professor Van de Graaff. Webelements.com, go ahead and jot that web address down. It's pretty easy, Web Elements. Don't go to webelement.com because that's a fake website. But webelementsplural.com is the one you want. And the reason that I wanted to draw your attention to that and just keep that handy in your web browser, every cell in the periodic table encodes all about the electronic structure of the atom. So, for instance, carbon, its location and the numbers in that cell, 6 and 12.011, those encode a lot of bulk properties for each atom, and then implicitly from those properties you can actually derive from first principles, if you know the electromagnetic interaction that we're studying today, you can derive the specific heat, for instance, or the heat conductivity of carbon. And carbon is a very important element for us because it's used in all kinds of thermal applications, like graphite and stuff. Okay, the electron theory of charge. Back in the days of the ancient Greeks, they knew that amber, which is fossilized pine pitch, if you rub it against your toga, it'll attract little tiny pieces of paper or little tiny pieces of papyrus and stuff like that. And we see static cling all the time. It's every time you take your laundry out of the dryer and you forget to put a sheet of bounce in there, some of it's going to stick together because of static electricity. It's basically in what the ancient Greeks knew was that rubbing amber, friction. They didn't realize that there were electrons, but they did know that rubbing it would produce electrical effects. As a matter of fact, the word electron is the Greek word for amber. So that's where we get the word electron. Now, the guy that figured out that electrons are actually tiny, tiny particles, his name is J.J. Thomson, a British scientist over in England. Here's a picture of him. And this is 120 years ago, and 125 when he was operating. And he had this device. Here's an image of it down here, kind of a line drawing, a sketch. This is a cathode ray tube, they call it. And what he did was in his day, they knew that there was a form of radiation coming off of item C here. This is a cathode, a positively charged or a negatively charged piece of metal, so it's connected to batteries or something like that. And they knew that it could be accelerated. And what J.J. Thomson did, he said, look, the name of the three kinds of radiation that they knew in his day, 120 years ago and more, so back about the time of Max Planck, alpha radiation, beta radiation, and gamma radiation. Now, gamma radiation is a form that came off of stuff like radium. And beta radiation, they knew that they could produce it in the lab with an electrical device. And alpha radiation was something that also came off of things like radium and other radioactive elements, which they had just started to discover. Marie Curie was one of the first ones to figure all that stuff out. So what J.J. Thomson said is, all right, I'm going to take my beta ray. And they knew how to generate them. And they knew how to direct them. Put them into a beam and, kind of send it through a little slot. And so only the electrons go in a certain direction. So you create a beam. And then he said, look, I'm going to send it between two parallel metal plates. I'm going to attach the positive plate or the top plate to a positive terminal of the battery, and I'm going to attach the lower plate to the negative terminal of a big battery, and then see what happens to the beta ray. So what he did was he had, so this is a picture of his device without the glass. I took the glass out of this, but painted on the inside surface at the far end of the glass was some phosphorus. So over here, right down in here, all right? And so this stuff, if the beta ray is negative, it'll be attracted to the upper plate, and it will light up in the upper half of this phosphorescent tube. And then if the beta ray is positive, then it'll be attracted to the negative plate, and it'll cause light to form over here. All right, so this is J.J. Thomson's experiment, and here's what he found. Bam. The beta ray went in, and it deflected towards the positive plate. And because of that, he knew that beta, and he figured out all the F equals ma, and he figured out that the mass was really small, and the electric charge was really small and negative. Matter of fact, he had a charge to mass ratio. The ratio of the charge of the electron divided by the mass. He was able to figure that exactly. And so he learned at that stage that these mysterious beta rays were little tiny negatively charged particles. This is counted as discovering the electron. Now, somebody else discovered the proton in the nucleus. That's a fellow named Rutherford. And we'll skip over that for now. But here's some concepts of electricity concerning electrons. In the metric system, the unit of charge is called the Coulomb. All right, now down here is a little ratio that I made up. 1 Coulomb in the metric system corresponds to 6.24 times 10 to the 18 protons. All right, a negative 1 Coulomb would be 6.24 times 10 to the 18 electrons. Okay, and so in the metric system, a Coulomb of charge is equivalent to that many protons. Now, a Coulomb of charge flowing through a circuit every second is known as 1 ampere. Make a note of that. I don't think I have it in my notes. 1 ampere of current is 1 Coulomb per second going through your circuit. And my wonderful students, your apartments and homes and your car, the wiring has capacities on the order of amps. And your cell phone, much smaller, milliamps probably, or microamps. Right? But your household current is amps. So like your air conditioner has its own circuit breaker. And the circuit breaker might be, rated for 30 amps. That's a lot of juice. 30 amps will kill you. It'll electrocute you. You'd be dead as a doornail. All right? But so amps are what kill you, not voltage, but amps, because you're getting zapped by a lot of electrons moving through your body. Minus 1 Coulomb, of course, is the same number of electrons. Because protons are positive, electrons are negative. And that's what we call the metric unit of charge. Now, the other way to measure electricity or electrical charge is simply to count up how many fundamental charges you have. Now, the fundamental charge, the symbol for it is E. It's the smallest charge in nature, and it's the charge on the proton. So E is, in terms of coulombs, E is equal to 1.60 times 10 to the minus 19 coulombs. So 1 proton is a very, very teeny fraction of a coulomb. So our human scale current and charge capacities are measured in coulombs and amperes, and that translates to zillions and zillions of protons and electrons, moving one way or moving the other way. Now, in normal wiring inside your house, inside your phone, the protons don't move. It's mainly the electrons that move. And the reason for that is that the mass of the proton, it's not in the outline, but you can make a note of it, the mass of the proton is about 2,000 times more than the mass of the electron. So in terms of F equals ma, the electrons are much easier to move, and they do move. The fundamental charge, E, is normally what we use when we're talking about atoms and electrons. So in the periodic table, for carbon, the number 6 tells you how many protons are in the nucleus. And so the charge would be 6e in the nucleus. And the electrons orbiting have a total charge of minus 6e. All right? But you can write it in terms of coulombs, but it's much handier to use the fundamental charge when you're talking about atoms and stuff. So let's talk about atoms. All right? So we know about atoms now. Professor Rutherford and Professor J.J. Thompson and Professor Chadwick, a bunch of other people figured out the basic makeup of the atom. So the nucleus is like a little bag filled with neutrons and protons. The neutrons are in gray, the protons are red, and the electrons are blue. So the electrons are outside the nucleus, so they're kind of orbiting around out there somewhere, depending on. And so this is a picture of helium-4. And you can have helium with 2 protons and 1 neutron, and that would be called helium-3, an isotope. All right, so this is what we think is the basic structure of helium, and most atoms are like this. And notice that I have kind of an irregular shaped container represented here, and that is definitely righteous because we don't think the nucleus forms. I mean, we always make pictures of it as if it were a sphere, but it doesn't hold together. It's not actually a sphere. We've smashed enough atoms together, enough nuclei together that we know it's not a perfect sphere. Matter of fact, if you think about this, electrically, like charges repel, unlike charges attract. So what is it that's holding that nucleus together? Because those babies want to repel. And neutrons, they don't have any charge, so they're just kind of floating around. They go whatever they want. So the question is, what's holding those together in the nucleus? And the answer to that we figured out about 90 years ago, is something called the strong nuclear force. There's another force of nature. So the forces that we've studied so far, gravitation, and now electromagnetic interaction. And then the third one is called the strong nuclear force. And that's what holds that's the bag. It's very short range, but it's very strong. It's strong enough to hold protons together from breaking apart. Okay, charging mechanisms and concepts of electricity. Yeah, friction. I mean, if you take a balloon, if you're at a birthday party and you have balloons and stuff, and you rub it against your shirt, then you can just put it next to your head and it will cling to your head, or it'll cling to the wall. That's static cling, right? And that's just by building up extra charge. So for instance, this young lady here in the diagram is combing her hair, and before she does that, her hair's got the same amount of electrons as protons. But after she combs, the comb strips some electrons from her hair. So her hair is net positive and the comb is net negative. All right, so that's how you charge. That's how the ancient Greeks, they would take a piece of amber and rub it against their toga and then pick up little pieces of paper with it. Okay? And this is the same thing. Okay? Now, another way of charging is just charging something up by contact. So this is, if you charge up that comb with some extra electrons, then you can charge something else up by touching the other object. So, a little piece of paper or anything like that. Now, this whole idea of friction gave rise to something called the Tribolelectric series. And so it was kind of invented by Benjamin Franklin and other people of his era. And so if you rub something from the top of the list with something at the bottom of the list, all right, so here's polyester, and then here's wool, nylon, human hair. So if you and here's let's see, saran wrap, vinyl. Okay, so plastics are going to be down here. All right, so balloons are going to be down here, and human hair, wool, nylon. Here's your toga up here. Or if you rub that balloon in your hair, and then it'll cling to something. That's how you get positive charge separated from negative charge. Okay? Now, a third way is something called polarization. So let's say that you have that comb, it's negatively charged, and you bring it near a piece of paper but don't touch it. All right? So you don't contact the paper, but you bring it near. What that's going to do is spin the hydrocarbon molecules in the paper, so the cellulose and all the other molecules and atoms, and they'll spin so their positive end is closer to the comb. And the negative end is further from the comb, because the negative of the comb wants to repel. Now, though you can't make the charges leave the paper unless you have a Van de Graaff. So you can do this with a comb, and you're not going to see sparks. But a Van de Graaff, yeah, you'll see sparks if you juice it up to high enough voltage. And if you go to one of these science museums, all you got to do is type in Van de Graaff in Google, or better yet, type in Van de Graaff in YouTube, and you'll see tons of demonstrations. Like they have they have some really huge Van de Graaff at the Boston Science Museum, and just huge bolts of lightning that they can produce with that. And that's that's when polarization breaks down, you get sparks. But if you don't get sparks, this paper will be attracted towards the comb. And that's how it works. Now, here's another thing that you can do at home. And I was thinking about doing a video of this. I've never done a video of this, but you can do it. You charge up a comb, or just rub it. If your hair's a little greasy, don't do that. Just rub it against your shirt or a towel or something. And then get the water in and this will work in the kitchen. Just get it to a very thin. You don't want drops. You want a stream of water. All right? And then you bring the comb next to it, and you'll see that there's a net pull force to the right from the comb. And that's because of polarization. You polarize the water molecules. So they get a little bit. Now, they don't, you can't, if you get the comb too close, you'll screw it up. But if you just bring it close enough, not too close, you'll see that water dip over to the, over to the right. Call it.
Is it as noticeable as in the picture?
It is. Yeah, you can do it. You can do it in your dorm room or, anywhere, anywhere you want, in the kitchen. It will work. I guarantee you. Unless you got like a lot of, your comb has to be clean. So run it under hot water and then let it dry off. Get all the, conditioner and, goop of that kind. Some people put a lot of goop in their hair. But otherwise, yeah. And, you could do it with a balloon. Just blow up a balloon and do the same thing. Just rub it against your shirt, and you could do it with anything with plastic. You could do it with a ping pong ball, probably. I've never tried that, but you probably could. Now, electric field lines. Here are the electric field lines from a Van de Graaff generator. There's positive charge that accumulates on that metal sphere, and if your hands are connected to it like those young ladies in the photos, the positive charge will go into them by contact, by conduction, and then it will go into their extremities. and one of your extremities is up here. And you know, when we were over there doing that, they could even feel the hair on their arms, go like this, just stand up on end. It was really working well. It depends on how humid the air is and stuff. Okay, so these are the electric field lines. Now, what that tells you, the electric field lines tell you the direction of the electric field lines, make a note of this, is the direction that a positive test charge would move. So if you have a lot of positives in that metal sphere, and you come nearby it with another positive charge, it's going to be repelled away. So the field lines all point away from the sphere if it's positively charged. Now here's a negatively charged sphere. All right, go ahead and make a, and this, let's just say that we got a bunch of electrons. We've done some tribolelectric separation. We've got electrons on this one. So this sphere is negatory. In this case, the field lines go inward. So the general theory is field lines go from positive toward negative, if they can. And so here's the Van de Graaff. And if they, if there's no negatives out there, they'll just keep on going. They just get weaker and weaker. They get further and further away. And the same thing here. The closer in, the tighter the field lines are together. That means that the electric field is stronger. All right? So the hypothetical positive charge at rest, it would want to move inward along a radius. All right? And so the electric field lines are defined by that behavior. Whatever a positive test charge, that hypothetical positive charge, so small that it doesn't affect the distribution of charge on your metal sphere. Okay? It's like a proton. And a bunch of coulombs on your sphere, and one proton's not going to do much damage to the distribution of charge on the sphere. All right, so that's a spherical array. So we have the typical example here, Van de Graaff, positive, and then the oppositely charged, negatively charged sphere. Now, what happens if you have a positive and a negative near each other? Well, if you think about it, if you have positive one of these near one of these, then the positive lines, the field lines from the positive, they'll want to go over towards the negative. So if they're right next to each other, they'll go straight across. So if this one and this one are right next to each other, then in between them you'll get field lines going straight across. But above them and below them, you'll get kind of a, well, here's what it looks like. There's what it looks like. This is what we call the electric dipole. So right in between, okay, I have my positive on the right, my negative on the left. The field lines go straight across from positive to negative. And then out here to the left of this negative, they come straight in. And over here to the right of the positive charge, they go straight out to the right. Now, in close, the field lines look spherical. So right in here, this first set of arrows, they look spherical, like a porcupine or bicycle wheel spokes. Same thing here. In close, the field lines look like just, a regular negative charge. But when you get, like halfway, now you don't have any spherical symmetry anymore. Yeah, this is what we call dipole symmetry. Okay? And here's another picture. This is actually the one that you should try to sketch. All right? And the reason that this is important, my wonderful students, is that hydrogen is a positive and a negative. Proton and an electron. Now that electrons moving around very high speeds, and these ones we're thinking of as being fixed in space, but these are the field lines. It looks kind of like a science fiction movie, kind of like almost like a spider web. All right, but right here in the middle, and notice that everywhere along this center line, the vertical symmetry line between positive and negative, go ahead and add that to your sketch. Add a vertical line, dashed line right down the middle, all the way from top to bottom. The electric field line at that symmetry line is to the left. Now, if you're away from the symmetry line, like over here, you're looking a little bit southwest. If you're at the symmetry line or away from it to the left, like right here where my cursor is, the field lines are northwest. If you go up here, if you go on the symmetry line anywhere here, the field lines are going right to left. They're pointing westward. If you go over here, straight above the negative, it's it's a little shaky here. You got like northeast direction. But right along that symmetry line, bang, everything. And that's because if they're the same size charge, then the field line from each will balance perfectly, and you'll get straight westward field lines right here. But just for this part. Okay, the other symmetry line is the horizontal symmetry line between positive and negative. And everything on that one, on the symmetry line, it's straight to the left. Actually, this other diagram shows this better. Oops. Okay, this one. On the horizontal symmetry line, everything out here is to the left, getting bigger. And then, in between, everything is to the left, westward. And then once you clear the other side out here past the positive, now everything is pointing to the right again. Okay, so you have kind of a flip in the direction of the field line along this particular symmetry line. All right. And so here's this is what we call the dipole field. And it's actually the same as a magnetic field. Here's a compass. Here's something I sometimes do, a little demonstration in lecture. A citrus battery, and those of you that are in elementary education majors, you can do this in your elementary school classroom. You take a paper clip and a piece of copper wire, has to be two different kinds of metal, and you put it inside of a lemon, or even a potato will work. I've done potatoes, I've done lemons, oranges, and grapefruit. They'll all work. And then you take your wire and you wrap it around a little compass. And then you connect it. So you connect it to like the paper clip, and then you stick the paper clip into the lemon, and electricity will flow. So electrical conductors, the electrons are relatively free to move throughout the material. So they'll move, they'll repel each other, and they'll end up moving. So if you have a spherical object made of a conductor like a metal, what that means is if you add electrons to the metal, they'll repel each other and they'll evenly distribute themselves on the surface of the sphere. Now, if you have something other than a sphere, they won't be symmetric. But if you have a sphere, they'll just back up from each other until they're feeling just right. And so that everything's mutually repelling. Okay? So they'll tend to dissipate. Here's some examples of conductors that we've mentioned. Metals. Graphite is a pretty good conductor. Carbon. Any kind of an ionic solution. In other words, a lemon, the acidic vinegar, even salt water has ions because the salt is dissolved in the salt water. Your body is filled with ions. If you've been in biology class, you know that ions are essential for making everything work in your body. The cells, your heartbeat, the muscles have to fire at a particular rate. So here's the famous citrus battery example. And you can tell current is flowing because it'll form a little electromagnet over here. So you wind it around the compass, and then you connect it, and you'll see the compass needle go, it'll line up with the coil instead of lining up with Earth. Because that coil is going to be, even with really pokey current, that coil is going to be plenty strong enough to overcome the magnetic field of the Earth. So, so the coils make an electromagnet. Now, the opposite case is just like with heat. Some substances conduct heat really well. Others, like styrofoam, not so much. And that's what we call an electrical insulator. Glass, most ceramics, plastic. And so that's why we put a little sheath of plastic around a wire, because you don't want the electrons in the wire to jump into your body. And to prevent that, you coat it with some plastic. So adding charge, they don't really go anywhere. So if you have a plastic sphere or a plastic comb, if you can get some electrons onto it, they're not really going to go anywhere unless you touch it to something positive. So if you touch it back to your hair, then the electrons are going to float into your body, and then you're going to. And if you're on the ground, they'll go into the earth itself. So examples of this are glass and wood. Diamond is actually an insulator. Same substance, different crystalline structure. It's not so easy to move the electrons. You could do it, but it's not that efficient. And then, of course, there are substances called semiconductors, which they'll conduct or insulate depending on, if they have a voltage applied to them. And these are the things that we have in computer chips. They're made of semiconductors. So under certain conditions, you flip on a switch, it'll permit current to flow. You turn the switch off, the current stops. And that's how all the digital stuff, and then you pack a zillion of those things onto a little chip, and you've got a computer. It makes everything zeros and ones, ons and offs. Now, let's just do a little bit about Professor Coulomb for the last 5 minutes of lecture. And then we'll dismiss, and everything that we talk about today will be on the exam. So we just have a little bit more. Professor Coulomb started out as a military engineer. He moved from France down to Martinique, an interesting guy. And then in 1776, he moved back to Paris and became an academic scientist. He got, I was reading a biography of him, and he barely escaped getting his head chopped off in the French Revolution. I mean, they were chopping everybody's heads off in the French at the end there in the French Revolution. But he kept his head. He developed a balance for figuring out very small forces. It's called a torsion balance, and it twisted horizontally. So, like the gravitational balance we use, it goes like this. It tilts like a seesaw. His was not built for gravity. It was built for electromagnetism. So he arranged his charges next to each other, left and right, and he figured out a way to make a balanced twist. And the twist angle correlated to the force, and he was able to figure out the force law. So the torsion balance, he figured out the force and the distance relation between them. And what he found was that the electromagnet, everybody, Ben Franklin, he's about the same time as Ben Franklin, right? 1776. All right. And so people were studying electricity. And before that, Professor Galvani and Professor Volta over in Italy, they're the ones that discovered the conduction of electricity from between two different kinds of metals, and that's how they've figured out how to make batteries, the voltaic cell. So here's what he found. He found that it's similar to universal gravitation. So the symbol that we use for electric charge is little q, sometimes big Q. And so you got to be alert to distinguishing between heat and electric charge. He found that they go charge the interaction goes charge to charge, so it's a pairwise interaction, and it depends on how much charge you've got. So in other words, how much you've rubbed it on your toga. All right, and also he found that it depends on the distance apart. And this is the formula that he found. He found that you multiply the charges in the numerator, you divide by the square of the distance, and to make newtons out of it, you put a conversion constant, K. That's called Coulomb's constant, lowercase k. But unlike gravitation, there are two kinds of electric charge. Now, in gravitation, you just put the two masses together, they're both positives. Electromagnetically, no, you got positives and negatives, and because that's the case, you have charges that can repel. Now, we don't get repulsive gravity except in science fiction movies. All right? But repulsive electrical forces, yes, we do. All right? Now, I'm going to give you, for homework this weekend, some very, and we'll talk more about electromagnetism after Thanksgiving. Do you know that our next lecture is going to be after Thanksgiving? But I'll give you a little bit of homework on these concepts for this weekend. It will be on the test. It'll be fairly cinchy, and some extra reading as well. Okay, you're dismissed, and I'll see you guys on Tuesday for the exam.